Okay, this is a short video about rates of change in graph behavior. So let's just start by looking at a graph and we'll be able to define some of the terminology I'd like to share through an actual example. So on the coordinate plane, I'm just going to go ahead and draw in a function. So we've talked a little bit about types of functions and what they look like and all that. So let's just graph a function. And I'm going to have this function kind of clearly pass through a couple points to make our discussion a little easier. So let's go ahead and get this guy in here looking something like that. So for this function f, which I've sketched before us, we can talk a little bit about terms such as where the function increases, where the function decreases, if there's any interval over which the function is constant, if there's a maximum or a minimum value, and that sort of thing. So let's start with the words increasing and decreasing. So where is the graph increasing versus where is the graph decreasing? And to get into this idea, we'll start talking about the other topic I wrote here, which is rates of change, and it's this idea of slope. So basically, when we think about increasing, we think about it as having a positive slope. So in general, the visual behavior of the function would be a slope going uphill or a positive slope. And then in contrast, that means that we've got a negative slope. So just looking at this function, I'm going to make sure we're all kind of clear on a couple points. I didn't draw this super easy to tell. So let's say that this peak right here occurs around -2, and then this little valley, let's say, occurs around 1. So would it seem logical to you all to say that from -infinity all the way until -2, the slope of the function is positive? Now, I'm not saying how positive it is, right? I'm not saying it's like a slope of 2 or 3, but I'm just saying it's positive. So that would be from -infinity all the way till -2. And I'm using a parentheses at -2 because it turns out right at -2 for a split second, the slope is actually going to be 0 because then it switches to be decreasing after that point. So then it switches to go downhill for a little while. So I could describe that red space that I just outlined on the function to be the space between, but not including, -2 and 1. So that's an interval of x values over which the function has a negative slope. Then again, it turns out at 1 for a split second, that slope is actually 0. So it would be mirrored by like a flat line. And then you can see the graph turns around and again goes back to positive. So analyzing the behavior of a graph in this way, it's not a super huge component of our class, but I love to talk about it early on because it starts planting some strong foundation for calculus. And I know a good number of you will either go on to like a business calculus class, or for some of you after a little bit of trigonometry, you'll go on to more of a calculus with analytical geometry for math majors or engineers or pre-med kind of folks. So getting those ideas in place now will just make us even more prepared for these topics when we learn about them more in calculus. So that's just analyzing the function from an increasing, decreasing perspective. The other two words I brought up were max and mins. Now, with the graph that I've drawn, it's not like this graph has an easy to identify total or absolute max or min, but we can see that there is a relative max point right here, right? Because relative to the points around it, it's a pretty high point. And similarly, we have a relative min right here because relative to the points around it, it's a low point. So I'm going to say that we've got a relative maximum. And I didn't give you guys a y scale, so let's just say at x equals -2. If I had told you the y value, we could have written it as an ordered pair. And then we'll say similarly, we've got a relative minimum value located when x is equal to 1. So that's kind of a fun way to analyze functions, just by looking at them from this increasing, decreasing language, and then also from max, min language. So I'm just going to do two more examples, and then we'll call it good with this idea. But let's look at another graph that's going to be more piecewise. In a previous video, we've looked at what we call piecewise graphs. So this next graph on the coordinate plane, I won't give you the actual equation that was used to create the graph, but we'll just stare at the graph itself. So this time we have a line pointing downhill, and then we've got a horizontal line, and then we've got a line pointing uphill. So I'm just drawing our function like that. Let me identify, hopefully a little bit more clearly, some good x points on this graph. So same questions. Let's talk about increasing, decreasing, and then one point that I didn't ask about in the last example because it didn't apply, but I'll throw it in here, will be constant. And then if we want to, we can talk about the idea of some relative max and mins. But let's focus on the increasing, decreasing, constant kind of things. So as we walk through the different intervals of this function, let's just go from left to right. It looks like this first interval, which goes from negative infinity all the way till -2, could be understood to have a negative slope. It's like you're going downhill from left to right. So let's say that the function, which again, this graph represents the function f, we can say, is decreasing from negative infinity up until, but not including, -2. So we don't include where it ends at -2, because typically at that point it's doing maybe two things. Then the line becomes horizontal for a moment. So if you think about this like running on a treadmill, we've got a constant slope for a minute, right? So another way to say this would be it's neither increasing nor decreasing. And that's in between -2 and 2, because then at 2, the graph begins to go uphill. So now we're back to this idea of a positive slope or increasing function. So this guy would be increasing from 2 to infinity. So I just wanted to throw in that idea of constant for a moment. Increasing, decreasing, constant. And then let's look at one more. This time I'm going to drop it back to more like our first example, where it's what we call polynomial. And in case you've got some experience with quadratics, you likely do. This is going to be a quadratic example. So again, we give ourselves the coordinate plane, and I'll sketch in our function as something like this. So let's again think about increasing, decreasing, constant, and then I'll throw in one last idea. So parabolas, or quadratics as we call them when they're graphed, parabolas have a vertex point, which means that this function is doing one thing until it reaches the vertex, and then it switches and does another. So I keep using the same colors to refer to increasing and decreasing. Increasing is a positive slope, so green seems like a good positive color, and that would be from 0 to infinity. And then the function would be decreasing right before that. So I could say it's decreasing from negative infinity to 0. And probably some questions we have as I just write down these intervals with you is remembering that intervals are spans of x values. So as we're talking about the interval from 0 to infinity, I'm really thinking about the values from the y-axis all the way to the biggest number I can imagine, and that all covers where the function here is increasing. And then decreasing was from the smallest number we can imagine all the way till the vertex at 0. So the intervals are intervals of x values that we're using. Cool. The other thing that you can talk about related to graph behavior is actually something called a rate of change. So I'm going to bring up slope for just a second. We've been talking about increasing and decreasing as positive or negative slope, respectively. Slope in the past we thought of as rise over run, right? And this worked really well when we talked about linear functions because linear functions have constant slope. But more generically, this can be thought of as a change in y, right, over a change in x. And actually in the past even we had a slope formula which was take the difference in the y values and divide it by the difference in the x values. So all I'm going to do is say this is true from everything we knew from the past with linears. This is now an idea that we can use to find the average rate of change. So if you ever encounter a question that says find the average rate of change, our good old slope formula from the past is able to do that. Let's say in this current parabola that we have graphed in front of us, I asked us to find the average rate of change between, let's say, like 1 and 3. So I know I haven't given us any specific values or equations yet, but would your guess be that the slope in the purple interval I just highlighted, would that slope, do you think, average out to be something positive or negative? And you might kind of go back to the fact that we've colored that portion of the function in green, right? So we already said it was increasing. So I would anticipate that the average rate of change over that purple interval would be a positive because it's all in that increasing interval. But let's prove it. So I'm going to give you a few more details now that I've asked a slightly different question. And I'm going to give you the actual equation of the function that I just drew. So the equation of the function could be, it was a parabola. So let's say it was x squared minus 2. And our goal is to find the average rate of change from x equals 1. Let's go from x equals 1 all the way to x equals 3. Okay. And the way we do that is the average rate of change is equal to basically the change in the y values that we're looking at divided by the change in the x values. Okay, well, we already have the x values. Those were given to us, right? We were given an x value of 3 and 1. So let's just take 3 minus 1. I'll treat this as x2 and this as x1. But that means we've got to find the y values that correspond to those x's. You can do this a couple different ways. I think one way that people like is this idea of a table. So when x is equal to 1 or when x is equal to 3, the y value is found by plugging it in to the equation of the function. So of course in this example we were told the function is x squared minus 2. So if I plug in 1, I'm going to scribble for a minute, that just means anytime I see an x in the function, plug 1 in. So that means take 1, square it, and subtract 2. That is the same as 1 minus 2, which sounds like negative 1. So when I get x equals 1, the output should be negative 1. So I'll go ahead and slap on negative 1 for my y1 value. And then let's do the same thing for when we plug in 3. Take 3, throw it back into the function. That means take 3 and square it. That's 9. And then subtract 2. So we get back 7. So the y value that corresponds to x being 3 would be 7. So I need to take the difference in the y values and divide by the difference in the x's. just so it's super clear, because this could be a little confusing here. Basically what this means is when x is 1, y is -1. When x is 3, y is 7. And I went ahead and took the first point to be the x1, y1. So you can see me using x1 as 1 and y1 as -1. And then I went ahead and let the second point be my x2 and my y2, my second x and my second y. So I used 3 and 7, where the formula called for x2 and y2. So let's go ahead and work out the arithmetic here. 7 minus -1 would just be 8. 3 minus 1 would just be 2. 8 divided by 2 is 4. So the average rate of change for the function over that interval is 4. And 4 is positive. So let me go back to our graph real quick and get your guys' buy-in on this. If I go back to the graph, again, this was a rough sketch that I showed here. Would it seem logical that between 1 and 3, from my very imperfect sketch, that the slope could be +4? Seems like it. And if you didn't feel super confident, feel free to throw it into Desmos. That's already something I've started using a little bit in the videos. If you go to Desmos, desmos.com, you can graph this function for yourself and take a little look at the slope. So that's a bit about the behavior of graphs and also the average rate of change.